This is, after all, a class on computer vision, so let's do some example of PCA with images. And possibly the most classic example is using PCA for recognizing faces, so-called eigenfaces. Before we actually look to implement that, I want to make a point about how you can very, very quickly with PCA run into some computational problems and then how to get around those computational problems. So what is a typical image resolution? Let's say it's, I don't know, 1,000 by 1,000, which means I'm living in a million-dimensional space. Yeah? Well, let's say we're a little more modest. Let's go down to 100 by 100 pixel. I'm still in a 10,000 dimensional space. And remember that when we're computing these eigenvectors and covariance matrices, we are operating on the dimensionality of the data. So imagine I have a data matrix here, which I'm going to call P. And remember what I do. Along the column is an entire data point. So in the two-dimensional space, it was xy, 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 which means that when I compute the covariance matrix, it's only 2 by 2, and the eigenvectors are only 2 by 2 calculations. But now imagine I've got an image in here. Well, first of all, how do I get an image into a column of a matrix? Well, I just take all the pixels and I string them out into vector form. So every row, just keep tacking them on. And then I get, for example, a 10,000 or a million dimension number of rows here. And that's a pretty big matrix, because now I've got to compute the covariance matrix of that. So that's 10,000 by 10,000. And then I've got to compute all the eigenvectors. And I can't control how many eigenvectors without using some other optimization techniques. And now I'm in for a world of hurt. So I've got this big dimensional problem here. But I've also got a dimensionality problem potentially here. I don't know how many data points I have. But typically with images, you don't typically, when you're doing things like PCA, have millions and tens of millions. More often than not, you have fewer data points than you have dimensionality. And so what we're going to do is we're going to look at a trick that solves the smaller of these two problems. So by all means, if you're living in a four-dimensional space and you have a million data points, then what I'm about to say isn't relevant to you. But if you have a relatively small number of data points in a very high dimensional space, we need to be very careful here. So again, the covariance of this thing here is going to be m by m. And if m is very large, on the order of 10,000 and 100,000 and a million relative to the number of data points, then the memory and the computational demands of PCA can very, very quickly be prohibitive. Now, it turns out you don't have to solve the harder of these problems. In fact, you can solve the simpler of them. So imagine I've got an m by n matrix. And if we just use PCA blindly, we are stuck with that m dimension for doing covariance matrices and eigenvectors. But if n is smaller, it'd be awfully nice if I can solve in some ways the smaller of the problem. And of course, it turns out that you can. So when you build these, when you're doing PCA, if your dimensionality is significantly, in fact, even a little bit larger than n, here's the trick you're going to do to save yourself some memory and some computation. Compute the wrong covariance matrix, C hat, which is D transpose D. So first of all, D is M by N, Mary by Nancy. And that means that C hat is N by M, where now N by assumption is going to be smaller than the dimensionality. So this matrix hopefully is more manageable. Now, that's not the covariance I want. I want this covariance matrix, and in particular, I want the eigenvectors of this. But let's think about this because it's more manageable. And in particular, let's compute the eigenvectors of this smaller covariance matrix. And let's see what it can tell us about the eigenvectors of the covariance that I actually want. All right, what is the eigenvector of this covariance matrix C hat? It's just D transpose D, that's the covariance matrix, times E is lambda E. Good. Let's multiply both sides of this equation by the data matrix D. So I've got D on this side, and I've got D here. Of course, the lambda is a scalar value, so I can bring the D inside. Let me just do the parentheses here. So I've got D transpose times DE is equal to lambda DE. What is D transpose? It's the covariance matrix. In fact, it's the covariance matrix that I want the eigenvectors of. And now look at what I have. It says here that the vector DE is a scaled version when it is multiplied by C. What is that? That's the eigenvector. That's amazing. So now I compute the eigenvector of the smaller matrix, the n by n matrix. I multiply that by my data matrix, and that is the eigenvector of the covariance, of the big covariance that I want. So what that means is that I can solve the smaller of these two problems, more memory, more computationally efficient, and then I can still get the eigenvector by simply multiplying the eigenvectors that I calculate by the data matrix. And this is really important because if you're going to use PCA on images, you're going to have to use that trick. And we're going to see the use of that for face recognition, so-called eigenfaces, when we come back.